Hello friends. So welcome to part 5 of the lecture series on the filter design. We have already completed IIR filter design and we have already talked about some differences of IIR and FIR filters. Now we will start in this section on this part with the FIR filters. So what is the meaning of FIR? The meaning is finite impulse response. So if we have any system which is a digital system or a discrete system having impulse response Hn, and if Hn is non-zero for finite values of n only, then it is FIR filter. Okay. Now, as we have seen that in the first part itself, I have taught you that whenever you will find the Z transform of this FIR filter, then Hz will have pole only at z equals to 0 or z equal to infinity. That is, no pole is between z equals to 0 and z equal to infinity. And we also know that ROC is entire z plane except z equals to 0 or infinity or both or none also, because if delta n Hn is equals to delta n, then in that case ROC is entire z plane. Okay, 0 and infinity are also included. So except z equals to 0, z equals to infinity or both or none. Okay, now we have seen this thing and I'm repeating it again because it's a very important property, that when Hn is FIR, then Hz, that is its Z transform or the transfer function of the system, will have poles only at z equals to 0 or z equals to infinity. There is no pole between z equals to 0 and infinity, and ROC is entire Z plane except 0 or infinity or both or none. Okay. So now let's look at few properties, because these kind of properties which I'm going to tell you here can be asked in a single marker question in GATE exam or any other competitive exams for electronics student. So the property is, now as we know, the stability of the system means summation of mod of Hn minus infinity to infinity should be less than infinity, and since for FIR filter Hn is non-zero only for few values of n, so FIR filters are always stable as they satisfy the condition given in equation number 1. Okay, because Hn is non-zero only for few values of n and always it is a finite value, so the sum will also be a finite value. Okay. Second, as we know that IIR filter can never be a linear phase. So the property of FIR filter is that FIR filter can be designed with a linear phase. Okay. Next property. Now this is a very important property. Now let's look at this property. This is a very important property. Now as we know that IIR filter has a pole, always has a pole. So Hz of IIR filter, so let us take Hz of IIR filter as HIIR Z. Let us take a simple example, A upon 1 minus B Z inverse, a simple example. So we will say YZ upon XZ is equals to A upon 1 minus B Z inverse. So by taking, we can say that A times of XZ is equal to YZ minus B Z inverse YZ is equal to AZ. Now converting this into a time domain equation, we will get that Yn minus B Yn minus 1 is equal to A times Xn. This implies Yn is equal to A times Xn plus B times Yn minus 1. So a very important conclusion is that the present value of output in IIR filter, the present value of output depend on, we can see that it is depending on the past value of output. Okay, and here we can see that it is depending on the present value of input also, and there can be other past value of input and other past value of output also, because I have taken a simple system, so that's why only these two terms are coming. So if I write a normal or a general form, then it will be A times of Xn plus A1 times of Xn minus 1 plus A2 times of Xn minus 2 and so on, plus B times of Yn minus 1 plus B1 times of Yn minus 2 and so on. So present value of output in IIR filter. So write this is a very important property of IIR filter. So for IIR filter, present output will be equal to, or I can say that present output depends on present and past input and also past outputs. And we know that you have seen in the system design, so you have already studied the block representation in the signals and system, block representation of the system in the signals and systems, and in controls also. So this is actually representing the feedback, and this is representing the feed forward. So I think you have studied that. If you have not, then please comment here and I will be preparing a video on that also. That's a very simple topic of signals and systems. So this is feedback and this is feed forward. Okay, so since the present output is depending on the past outputs, so this is called a system which has having feedback, and this is called a recursive system. So IIR filters are always recursive system because there always be a pole, and pole always shows a feedback path. Okay, so this thing, I hope that you have already studied the the system design, and that's why I'm not explaining the things here. I will be making a video on that also. So this is a recursive system. So IR filters are always recursive system, but the FIR filters, since there are no poles here, in FIR filter, there is no pole. There is a pole are at only 0 and infinity. So HZ will be of the format A times A plus A1 Z inverse plus A2 Z to the minus 2, A3 Z to the minus 3, that's all, something like that. So if I write YZ upon XZ is equal to A plus A1 Z inverse plus A2 Z to the minus 2, A3 Z to the minus 3. So I can write Yn is equal to A times Xn, A1 times Xn minus 1, A2 times Xn minus 2, A3 times Xn minus 3. So I can see that the present output is depending only on the present input and the past inputs only. And such kind of system where there is no feedback path. So there is no feedback path here. So such kind of systems are called non-recursive systems. So FIR filters are non-recursive systems. Okay. So these are very, very important properties of the FIR filters. Okay. So in the next part, we will be looking at the characteristics of the FIR filters and what should be the characteristics of the filter so that they are of linear phase. Okay. So thank you guys. Keep sharing these lectures and give us your feedback